Okay, so I welcome you all. So in the previous video, we just looked at how to find the total power factor, and we realized that when they ask us that, they're just indirectly asking us to obtain the total complex power. So we managed to do that, and we found the total power factor of the parallel combination to be 0.897, like this. So with that said, question B further goes on to ask us to say, calculate the value of the capacitance connected in parallel that will raise the power factor to unit. So a brief description for those of you that are bookworms and you just want to go and research. This is from the concept of power factor correction. So you can just look up power factor correction. Right. So what exactly are they even asking for here? So you are going to realize something, and that something is nothing but most loads that we have today are inductive in nature. And because they are inductive in nature, you get to realize that they have a very low lagging power factor. But we know that power factor is in fact just related to the real power over the complex power, which is what we did previously. Right, so it means in fact the real power is just the complex power, oh sorry, not the complex power, the apparent power times the power factor. In fact, this is another definition for real power. It is just the product of the apparent power times the power factor. So now, because most loads, they just have a power factor which is low, but keeping in mind that it is just between 0 and 1, like this, it can't exceed 1, it can't exceed 0. You get to realize something. You notice that because we just want to supply a constant power. So let's say we maintain this power to a load. If this keeps on getting lower and lower and lower, it means you are going to need a very big amount of this apparent power. But we know that apparent power is just in fact equals to the magnitude of the complex power. So now we know that complex power represented by both face, it is just V times, let me just use RMS value, times the RMS value of the complex conjugate. All these are just in phasor domain. So if you notice that, you can even rewrite this equation to just be equals to I RMS squared times the resistance. Or you can use this one. So now, if the power factor is small, it means you need a very big amount of this apparent power. And if you need a big amount of apparent power, you need a big amount of complex power. A big amount of complex power, since in this case we cannot change the voltage, we just want to maintain the voltage to be the same. So the only way this equation is going to hold true, if we have a big complex number, this is constant, is if we increase the complex conjugate of the current, which is just the same as increasing the current. So now, if you have a very big current, you realize that ZESCO is going to charge you a lot of money because you are wasting current to just maybe turn on a bulb which is maybe 100 watts and you don't want to use a lot of current. So what most companies that manufacture electrical appliances do is that they just want to make sure that instead of having a low power factor, they want to in fact increase it maybe to how much? We can say maybe as close to 1, maybe. Yes, so maybe we can say that we want the power factor to be just approximately equal to 1. It can't be 1, but it may be 1, and we know that the power factor of 1 is in fact of the type of the resistor, and in this case maybe it's just it means the current and the voltage are in phase. And if you have a very big power factor, we notice that we don't need the big number here because we just want this equation to hold true. This is a constant, we are varying these two. So if this is big, it means we need very little of this to make sure that the equation holds true. So now if we reduce this, it means that even this, the complex power, reduces. So if this reduces, because this is a constant here as well, it means the current reduces. So if we reduce the current, it means the ESCO will not charge us a lot of money. And because of that, we save up on money, and I think that is what we all want, saving up on money. So this process alone is called the power factor effect, and if we are able to find a way of reducing the power factor, and we do that by a process called power factor correction. So for power factor correction, we just want to reduce the power factor, not reduce, increase it to maybe unity, which is in this case 1. So one way we can do that is we can just connect a capacitor in parallel to the inductive load, and an inductive load it looks something like this. It is just in fact an inductor and a resistor connected at these 2 points, plus minus. So this is L and this is your resistor. So maybe you can just connect a capacitor in parallel like this. Then you can notice that if you had the current going here initially as I load, and now you have connected a capacitor, you just have the current of the capacitor going like this. So now what are we trying to prove here? We are trying to show that in fact the total current after we have connected the capacitor is going to be less than the inductive load here, which is going here. But if you go back to your mathematics, if you go back to your KCL, KVL, you are going to notice that this doesn't make sense theoretically. If you are at this node, the sum of the currents entering is equal to the sum of the currents leaving. So it means if you want the same current, not really the same current, but if you divide this current here and you still want to have the same current going through here, it means you have increased your current here. But because this is just in phasor domain, it makes sense. And if you want to see why it makes sense, you can just look at the phasor diagram of what we are talking about here. So we notice that the phasor diagram will look something like this, where this is just the real axis and this is the imaginary axis. So now, because the voltage, maybe we can just represent it like this. The voltage is going to be ahead of the current, because we said most loads are just inductive in nature. So for the current of the load, it will lag the voltage, but maybe we don't know what that angle will be. We can just call it theta 1. So we said we can connect we can try to connect a capacitor in parallel, and then we are going to notice that actually we're going to reduce the current and not increase it. But how that works is because the current of the capacitor is going to be at a different phase as compared to the current of the inductor. But again, we know that if this is the voltage source here, the current of the capacitor is actually ahead of the voltage by a phase of 90 degrees. So maybe the current of the capacitor is just going to be like this. So now if we wish to determine the total current now, which we are trying to say is going to be less than the current going through the load here, we know that we can just use the parallelogram law from what do we call this, statics. And if you add this like this, you're going to notice that the total is going to be somewhere there, and you realize that now this current total is going to reduce like that, and that is what we call power factor correction. Now, sorry we wasted a lot of time explaining power factor correction, but now we have an idea, and we can even find the value of this value of the shunt capacitor. It is just given by QC over omega times V RMS squared. Now you can even say that QC is just going to be the difference between Q1 minus Q2 over omega V RMS squared. So you notice that to use this formula, you in fact need three things. You need the value of the new reactive power divided by omega, right? And also the voltage squared, and it just has to be given in terms of the RMS, like that. So with that said, you need to obtain the initial reactive power, what it was before you changed the phase angle, and you also need to obtain the new reactive power, and then you subtract the two, then you just divide. So with that said, we realize that the total reactive power, I think we calculated it in the previous question. It was just given to us as 64K. No, not 64K. It is the other part. This is the real power. So it was given as 31.147K. This is just VAR. So with that said, we can even call this to be our Q1. So now the question reads, we want to raise this power factor to unity. So a power factor of unity means just equals to 1, but we know that power factor is just cosine of this angle. So if you take the inverse of 1, I think you just get this angle to be 0. So you know that you want to reduce your angle from what you had initially to a new value, in fact. Yes. So from here, once we know this angle, what we want to obtain is in fact the new reactive power. But like I said, don't worry about the formulas. All you need to do is use the power triangle. It will always guide you. Let it be your best friend. I know that it doesn't make sense to say you have an angle of 0 because it's just going to be lying along this. But for maybe pedagogic reasons, let's just call this your theta. So this is going to be your real power, and we're looking for Q. Yeah, so in this case, this P is a constant because in the explanation we gave, we said we want to deliver the same amount of power to a load, but we just want to be varying the complex power, and all those things, but this will not in fact change. So it means you just have to use the same value we had for the total real power, which is 64K. Now we are looking for the new reactive power, Q2. So we have found this angle to be 0. So if we have the opposite and the adjacent, it's a tangent function. So we just say tangent of phi is the opposite, will be Q2 over what are we looking for here? We're just looking for the adjacent, which is 64K. So it means Q2 is just going to be equals to 64K multiplied by tangent of 0. But I don't think you'll get anything when the tangent function is 0. You just get 0. So it means this is equals to 0. So it means even if we say QC is Q1 minus Q2, we just get Q1. It means QC is equals to Q1. So QC is Q1 is what now? It was just 31.147. 31.147 kVAr, like this. So now you can just find the value of the capacitance as this 31.147. Okay, remember it is QC over omega, but omega is just given by 2 pi times the frequency. So omega, the angular frequency, is 2 times pi times the frequency. So we were given the frequency in the equation, which is just 60. So you say 2 multiplied by 60. Sorry, okay, pi, yes. And then maybe you want the voltage, but in terms of the RMS value, but it has been given as RMS value already. Let me just square it. So if you do this correctly, let me just punch it on the calculator. So you say 120 squared times pi times 60, then times 2, then you just divide it by 31, it is 31.147 divided by this. And this is a very small number, so you just multiply by 10 to the power 3. Yes. So you obtain a value of 5.7 millifards as the value of the capacitance. Hopefully this video has been helpful to you, and now you have an idea or two. Thank you.